Welcome back for our second video and discussion board for this week. So we're going to talk about the generalization we kind of left off with in our other discussion board. So this is going to be Euler's formula for P and Q for a product of two primes, and it can be generalized. Here is the theorem that maybe you saw. P and Q, let them be distinct primes, and let G be the greatest common divisor of them. Then A to the P minus 1 times Q minus 1 mod G is congruent to 1 mod PQ for all A, where A is well, A is relatively prime to PQ, which really means A is not a product of P or Q because they're already primes, and A is hopefully smaller. So yeah, we're good. So what does this mean in terms of like our last example that maybe you were seeing on the board? So remember our last one, we did it mod 15. Which meant P equaled 3 and Q equaled 5. Well, in that situation, G equals the greatest common divisor of 2 and 4, which is 2, because 3 comes from 2 minus 1 and 5 comes from 2 minus 1. So any number A to the 2 times 4 over 2 is congruent to 1 as long as that is not a product of 3, as long as the greatest common divisor of A and Q, I mean, A is not a product of P and Q. So, and this number right here, this really means that A to the 4th power is congruent to 1 mod 15, as long as A, the greatest common divisor of A and 15 is 1, which eliminates numbers like 3, 5, and 10, as well as 6 and 9. If you look at all the other numbers, when they got to the 4th power, they actually hit this exactly on the head. So this is actually the really cool part about this, since A is everything that satisfies this. So we got to kind of keep this in mind as we kind of work through all this idea that these numbers right here end up actually causing all the problems. If you look in that last column from the previous video, they were the ones that actually did not satisfy. So this Euler's theorem is really, really powerful in that it lets us now apply Euler's formula in general, but in the situation where I have a product instead of just a prime value. So, and notice this works for odd primes, which is every prime besides 2. So we're ignoring the prime 2 because mod 2 is just, well, boring, and this works for everything. So let's go back to our crypto systems because I want to point something out. Again, this is where we're also going to have a difference. In the Diffie-Hellman key exchange and the Elgamal public key crypto system, both of them were reliant on A to the X, where X was actually my message. And that's what made it hard, is my message was my exponent. This is really problematic because if I have an exponent, then my message or X is just simply the thing that's not known. Maybe it's my secret, maybe it's my message, who knows, but it's the thing they're not known. A, B, and A, B, and P are all known values by everybody around. X is the unknown value, and therefore it becomes really hard to do. In RSA, we're going to switch it up a little bit. We're going to do X to some exponent. So X is now the unknown value, and we're going to raise that to a known exponent. So now I don't know the base, but I know the exponent. And in that situation, it's a little bit trickier because we're still trying to work our way through all of this. And what happens though if n is prime? So let's kind of examine this. I want you to help think about this. If n is prime, then it's a prime number, p is a prime, and e is some power. Again, so e is, I'm taking x to the power, and it's gonna be mod p, whereas p is prime. And e is any power where the greatest common divisor of e and p minus 1 is equal to 1. Okay. Then we know that we have an inverse mod p minus 1 because their greatest common divisor is 1. There's an inverse, namely d, and that d is actually what's going to give us it. And so the congruence x is if I raise both sides to the d power, it works because, so that's the problem. So if e and p are known, then guess what? It's easy to find x. So this problem is this is completely vulnerable if I'm just doing a prime number because I'm now the exponent is known. So that doesn't work. So the exponent thing works, the exponent being the unknown if we do a prime. But as soon as we're using a prime value for p, now it becomes really, really hard. I mean, now it becomes easy. If p is known, then finding the exponent is really easy. But if p is known and the exponent's the unknown, it's hard. Do you kind of see the difference? So if the mod is base p and the p is known, then it's actually really easy to compute because of Euler's lemma. So what do we do now? So let's just look at an example about why all of this Chinese remainder theorem and the formula we originally had coming back here was so important. That G equals the greatest common divisor P minus Q, then all of this is congruent to 1 mod PQ. Wait, it's congruent to 1 mod PQ? That's really, really powerful and useful because now it's essentially giving me the Euler's lemma to do later on. Now, I'm going to do, there is one really nice part about this, and I'll mention this in a little bit. So let's look at a congruence here. I'm trying to solve this congruence. X to the 15th to the 1583 is congruent to 4714 mod 7919, where I have a mod p. I have a prime number. So for this case, all I need to do is solve what's 1583 times d is congruent to 1 mod 7918. In other words, what's the multiplicative inverse of 1583 mod p minus 1? That's all we're doing. We can solve this. We have a whole bunch of extended Euclidean algorithms. Boom, we get it as 5277. Okay, so all I have now is x is congruent to 47145277. Okay, that's great. That's cool. Which is equal to this 6059. So one of my solutions to this thing is that x is 6059. It's one, that's my solution. So we found a solution, but that meant I had to do a bunch of extended Euclidean algorithm. And actually, the extended Euclidean algorithm is not that painful. So this was pretty easy if I left this out on the internet. So let me give you another proposition that we're actually now going to use. Suppose that x is any integer, n, a1, and a2 are any non-negative integers. In other words, they start at 1. They could be anything from 1 on. And let's assume that a1 is congruent to a2 mod phi of n, which, remember, is the number of prime numbers, number of values relatively prime to n. So let me just make a note. This is number of relatively prime to n. Values. That's kind of, okay. So for instance, but if that's the case, then their x to either of the powers is actually mod n is the same number. This is where this phi function, we did this when we did phi, this is the phi function we did earlier. We're now applying it again. So what we can do is actually use it to calculate things really easy. So in this case, I'm taking it mod 11. I'm doing this on purpose to do a really easy example. So here's our first question. What is phi? Okay, that's wrong one. What is phi of 11? Well, the good news is phi of 11 is known because it's a prime number. It's 11 minus 1, or 10. And because we already did this before, we already mentioned way back when we did this that phi of p is equal to p minus 1. Because every number from 1 to n is going to be relatively prime. 1 to n minus 1. So it's going to be 10. So then all I have to do here is actually 22 is congruent to 2 mod 10. Which means, based on this theorem up here, that 7 to the 22nd power is congruent to 7 to the second power mod 11, which is 49 mod 11, which is 5. So we got to our answer by simply breaking it down again to a much easier and simpler power by understanding how these theorems work together. So if you remember, this is something we kind of played with a little bit in discrete math. We talked about some ways to do exponential powers. This is actually one of the critical ideas that's beautiful and super powerful. The problem is it requires this phi of n, which if n is prime, easy. If it's not prime, not so easy. But it actually is, depending on the number of prime factorization of it. Now we have another proposition that goes along with this. So propositions are like mini theorems. So let P and Q be distinct primes and let E be any number bigger than or equal to 1 such that E satisfies this. So the greatest common divisor of E and P minus 1, Q minus 1 product is equal to 1. Then that means that the greatest common divisor is 1, they're relatively prime, it has an inverse. We're going to call that D. So because of this line up here, if their greatest common divisor is 1, then that has an inverse mod whatever thing it's relatively prime to. It also means that x to the e is equal to c pq. Then x is actually congruent to c to the d mod pq. So this inverse mod p minus 1 q minus 1 turns out to help us do pq. Huh, that's really crazy and cool. So a remark on that real quick, this actually gives us the algorithm to find this and do it super fast. We can find DE is congruent to 1 mod P minus 1 Q minus 1, and then compute C to the D. We can often make this even faster by going back to that G that we did from in the very beginning of today, which is the greatest common divisor of P minus 1 and Q minus 1. And if I take DE is congruent to 1 mod P minus 1 Q minus 1 divided by G, because it's going to be a factor in there. So it's going to come from one of them and leave the other one alone. And in fact, that's going to give us that number that we want to get ourselves back to there. So a to that power is going to get us back to 1. And this DE is congruent to 1 is actually what's going to help us undo all that and get ourselves back there. So to help you see that, let me work an example real quick. So let's look at the congruence x to 17,389 is congruent to 43,927. Yes, I'm dealing with bigger numbers here on purpose. And I'm going to go and I'm going to skip and do the hand wave over the Euclidean algorithm. Again, you should be using this to be doing it really quick, really easy at this point in time. And you can keep working on it. The nice part is our mod breaks down into two very nice prime numbers, namely 229 times 281. Here's the clue. I know that. If you didn't know that, finding that information would be actually very hard. Going back to earlier, we talked about prime factorization being hard. So I'm trying to tie these ideas back and forth in different times and build. This is why we cared about that prime factorization. This is where it really comes back to play. So our first step to solving this is to find d to the where 17,389 times d is congruent to 1 mod p minus 1 times q minus 1, which is 63,840. Which notice is really close to p times q, but we digress. Now what we do is we can solve this by doing extended Euclidean algorithm and find that d is equal to 53,509. From there, we take that number and we simply take our number on the other side of the equation, 43,987. So remember, I had this 43,987 right here, and I'm just going to raise that to this power right here, this d power. And I'm going to raise that to since d is equal to that, I'm going to raise it to the power, which gives me 14,458. And it turns out that that is my solution, is this 14,458. But our remark actually makes it easier because we can save a little bit of time, because the greatest common divisor of 228 and 281 is 4. So I could have divided 228 times 280 and gotten 15,960, which means I was solving d when it is a congruence of 1 mod 15,960, which again, you can do that multiple ways. D is equal to 5,629, which gets us the exact same answer. Some of you might be sitting there going, well, I got the same answer. So let me just kind of highlight those answers real quick, because let me circle them. So we have this answer right here. We have this answer up here. They're the same. And notice my exponents, though, are different. The bases are the same. Why do I care about this exponent down here, 5,629, over this exponent up here, 53,509? Even with our exponentiation process using the binary expansion, this is still way more complex than doing this step. So adding this one little part about that extra proposition where we can divide by the greatest common divisor to crank it down just a little bit smaller, it would make the extended Euclidean algorithm faster, and it makes my exponentiation faster. So these are the reasons we care about all these remarks and all these theorems, is they actually break it down and make it easier for us. But they are critical for us to kind of balance all this out. All right, let me clear all those out, and I want to just take you to your last problems of the day. So I want you to solve these two congruences. X to the 19th power is congruent to 36 mod 97. So your question is 97 a prime number? If not, you need to factor it out. If it is prime, it should be super easy. Same way, X to the 73 is congruent to 614 mod 1159. Ask yourself a question real quick. Are these prime or are they not? If they are not prime, then remember we have to use Euclid's thing, which means we have to do a prime factorization of the numbers. And if they are prime, then we're in a really good spot. All right, good luck. Show your work on the discussion board. I'm excited to see what you guys do. Let me know what questions you got.